Hello, everyone, and welcome to this week's SMaRT seminar series. This week, we are hosting Professor Ilias Bilionis. It's our pleasure to host him to this seminar. So he's a professor of mechanical engineering at Purdue University. He received his bachelor's and master's degree from the National Technical University of Athens. He was awarded the PhD in applied mathematics from Cornell University with Professor Nicholas Zabaris. After graduation, he worked as a postdoctoral researcher at the Mathematics and Computer Science Division of Argonne National Lab. He currently leads the Predictive Science Laboratory at Purdue University, which works towards accelerating engineering innovation through the development of AI-based models. His research is highly interdisciplinary, and he has received funding from various organizations starting from NSF, NASA, DARPA, and AFRL, and several industrial grants from Cummins, Eli Lilly, Ford Motor, and Facebook. In 2019, Bilionis was presented with the Outstanding Faculty Mentor of Mechanical Engineering Graduate Student Award for his service as a graduate student mentor. Additionally, he has developed data science course for the core mechanical engineering curriculum and has received the Outstanding Engineering Teacher Recognition Award 3 times. So with that brief introduction, please join me in welcoming Professor Ilias Bilionis for this. Ilias, the floor is all yours.
All right, thank you very much. I just want to mention a little bit, like a shout out to the data science course. If you are in an engineering school and you're looking for material to teach at the undergraduate level, teach your undergraduates basic data science, feel free to use my material and my online textbook. And the same thing goes for two other books that I have written, again online, for scientific machine learning, introduction to scientific machine learning, and then advanced scientific machine learning. You can find all of these in my web page, and really just use them. Okay, you don't even have to tell me. All right, I would appreciate it if you told me, but you don't have to. Okay, so today's talk is going to be about information field theory, and this is an approach that we have been developing for the past 7 years or so. It took a while to kick it off the ground, and it's only now that we have started seeing applications of these ideas. Now, the work was primarily spearheaded by Alex Alberts, who's now my postdoc, and he would be an excellent tenure track assistant professor if you have any open positions right now. So feel free to reach out to him or to me. I can introduce you to him. Okay, so basically, pretty much everything I'm going to talk about regarding the theory was done by Alex, with some part done by Kai-Rui Hao, who's also my PhD student, is now in China. The work of Alex basically will give you all the details all of what I'm going to talk about. My talk, because I want to cover pretty much 8 different papers, is going to be very superficial. I'm not going to go into the technical details. If you want technical details, ask Alex to give a talk. He'll be more than happy to do so, and you would have learned something. All right, so we're going to cover the basics of information field theory. I'm going to tell you what it is. I'll show you some applications, and then I'll show you some current work, ongoing work on hemodynamic and CSF flow reconstruction, where we have started applying IFT. I'm going to use IFT for information field theory. I'm going to use this acronym. We're starting applying IFT in that field, but we're not done yet. We're just starting, basically. So you'll see some preliminary results here from some really rough approximations of the ideal thing you could be doing. All right, so what is information field theory? It's basically Bayesian statistics over fields. And by fields, I mean functions of space and time, physical fields, temperature fields, pressure fields, velocity fields, strain fields, stress fields, stuff like that. And it was developed by Enslin, Thorsten Enslin, who's a physicist in Germany. And it was developed for nonlinear signal analysis in astrophysics. So basically here, he was reconstructing, he developed this to reconstruct astronomical fields. And if you want to get the background of how this theory started, go ahead and look at his paper. It's actually an excellent paper. Now, the key thing to understand in information field theory is that it uses mathematics of quantum field theory and statistical field theory, and in particular, something called Feynman path integral. I'm going to show you Feynman path integrals in a while. Now, in books like Statistical Physics of Fields or Quantum Field Theory for Gifted Amateurs, you can learn some of the basics of these Feynman path integrals at the level that physicists use them. So more intuitively than mathematically rigorously. There has been some work that looks into rigorously defining Feynman path integrals, but they remain notoriously hard to completely rigorously define mathematically. Okay. So as were developing information field theory, we basically reached the limit where we developed mathematics that we didn't quite understand if they exist in the sense, you would prove, let's say, in a real analysis course or in a set theory course. And Alex has been developing the mathematics that show that may basically make rigorous some of the intuitive notions that I'm going to show you today. All right, so how does it work? I'll break it down to a few steps. We'll go over the steps, and then we're going to dive into some of the details. So the first thing you do is you take your partial differential equations or ordinary differential equations, you take your physics, and you use them to construct a physics-informed prior over the space of physical fields. And that is basically a probability measure over a function space. And it looks like this. So we're going to be using U for the field. So U is going to be a function of space and potentially time. And then the rest of the parameters, the rest of the symbols I'm going to express later on. But what I want you to look at is this exponential divided by the z. This is a so-called energy-based model. So we're going to call that E, the energy, and the energy will encode the physics. And the z here is going to be the Feynman path integral, and it cannot be dropped. So we will explain that later. So the first thing is a probability measure over the function space that is of interest to you, the space of physical fields. The second thing you need is a measurement model. This is a model of the measurement process, and it basically connects the underlying unknown field to the data you observe. And we're going to call the data D. Once you have these two things, you're pretty much done in terms of the theory side, right? So you have your prior, you have your likelihood. If you wanted to ask, what do I know about the field given the data I have seen, you just write down Bayes' rule. You write it down formally, and part of Alex's work is to prove that whatever you write down makes sense mathematically. But once you have these two, you're done regarding the theory. Now we start with the numerical implementation, which requires basically discretizing the field. So you cannot work directly with functions. So you basically parameterize the field using some parameters, which I'm going to call phi throughout the presentation. This parameterization could be really anything you like. It could be Fourier series, it could be a neural network, whatever you like. The only complication is that if it is a neural network, you need to do more work to show that it behaves properly in the limit of infinite, let's say, neurons. And then you characterize the field posterior for the parameters, okay, for the parameterized version of the field, which we can write down with Bayes' rule. Okay. Once you have the posterior, you have two choices. We have developed two algorithms to sample from that posterior. One is based on stochastic green and algebraic dynamics, and it's described in Alex's paper. And one is based on stochastic variational inference, and it's described in Kairo's paper. Now, the catch here is that because of this Z, these are not simple characterization algorithms. It's not simple MCMC. It's not simple variational inference. it's actually nested versions of these algorithms. If you like, there is a stochastic gradient algebraic dynamics inside the stochastic gradient algebraic dynamics, and then there's a variational inference inside the variational inference. The details are in the paper, and Alex would be happy to explain more if you ask him to give a talk. All right. So here's how the physics informed prior looks like. Let's dive in and look at it. So here U is the field, it's a function, and we encode the physics in terms of an energy function. Now the energy function could be an actual energy function, an energy formulation of the problem you have, and I'll show you an example later, but it could also be the integrated square residual of the PDE, the same thing you would use in pins. And there is a connection with pins that I will show you later as well. Now, theta, here are the physical parameters to be calibrated. So your physical model, your PD or your OD may have some parameters. We call those theta, and they enter the energy function. Now, the beta parameter is what controls our trust in the physics. And let me demonstrate this with a stupid visualization. So here we're going to visualize functions as points on the real line. So the x-axis is functions. It's every point is a function. So try to imagine that. And then I'm going to draw basically this fictitious probability density that encodes the physics. Now, if you're pretty sure about the physics, you choose a beta that is big, and that basically creates a probability measure that is centered around the solution of your PDE or your ODE. Okay, that's what beta does. So if you take beta to infinity, this probability measure will basically collapse on a delta function that just picks up the solution of your forward model. In the sense of inverse problems. And in the limit of beta goes to infinity, you basically recover traditional inverse problems. But if you choose a moderate beta, you're basically saying, okay, I'm not so sure that my physics are correct. You know, maybe they are, maybe they're not. And if you pick a beta close to zero, you're basically saying, I'm pretty sure my physics are not correct. So this is one of the fundamental innovations and how we differ from the traditional IFT of Torsten. There are two things, actually. One is that we use this energy function to encode the physics, and the other one is this trust parameter that controls how much we trust the physics. Now, treating beta as a hyperparameter allows us to automatically quantify the trust in the physics. So we believe that IFT, and we have both theoretical and empirical evidence to show that. I'm going to go over the empirical evidence today. We believe that in this way, you can basically quantify model form error. So you have basically a framework that tells you, look, the physics you are trying to feed are wrong. And that corresponds to beta go to zero. All right, now here's the problem. The problem is this z. That's the Feynman path integral. You cannot drop it. If you want to find theta and you want to find beta, you cannot drop the z. Okay, that's the idea. And it looks like this. It's an integral basically over this exponential. All right, but the integral is not over a finite dimensional object. It is over a function. Okay, so it's over all the possible paths. If U was the state of the dynamical system, it will be over all possible paths. If it is a field, like a special field, it's over all the, let's say, temperature fields or pressure fields or whatnot. So it's a complicated thing. It's also known as a functional integral. And the catch is that, okay, we can write it down formally, but it doesn't always exist in the sense that it can be infinite. Okay. Now, in quantum field theory and statistical field theory, they do all sorts of tricks to get rid of these infinities, and they manage to get theories that are highly predictive. We can do the same thing, like empirically, basically use this idea to construct methods that solve inverse problems, but we're also trying to understand when these measures rigorously exist. All right, let me give you an example where this measure rigorously exists. This is going to be an IFT prior for the Poisson equation. So the Poisson equation, you can see it on the top left. It has an energy formulation through the Dirichlet principle. So the Dirichlet principle basically says that if you minimize this energy function subject to the Dirichlet conditions, you're going to get the solution of that PDE. Okay, that's what it says. And then we show in our paper that when you use that energy function in the way I showed you before to write down this fictitious probability density over functions, this basically corresponds to a Gaussian process that is centered at the solution of the PDE and has a covariance function that is controlled by inverse beta. So inverse beta, the trust parameters, controls the covariance. So the bigger the beta, the smaller the uncertainty, and the smaller the beta, the bigger the uncertainty. And it also has the inverse Laplacian there. Now, you can also see in our paper that what goes there is actually the Green's function of the PDE scaled by inverse beta. All right, and this is how the measure looks like. So for different betas, so for beta equals 1, you see here the blue line is the solution of the PDE that corresponds to the mean, and then you see some samples from this Gaussian process, and we just visualize the 95% credible interval. And you see that as you increase beta, you see this collapse on the solution of the PDE. Okay, so this is basically the intuition behind what we do. We construct a probability measure that is centered on the solution, but then we're allowing deviations from the solution. All right, now let me show you another case where this measure is rigorously defined, and this was done by Kai Rui in his paper. So you take here a dynamical system. So instead of U, we're going to have X, the state of a dynamical system, and X is going to be a function of time. And let's say that X satisfies this equation on the left, this ordinary differential equation, with a vector field F with parameters theta. Now, what we construct here is the integrated square residual. So we move the vector field to the right, we take the Euclidean norm and we square, and we integrate that over time. Okay, and we make this energy function that is conditioned on the initial condition of the state. So this x naught is basically the state at time 0, the initial condition. This is the equivalent of the boundary conditions in the previous problem. And then this x minus 0 is basically the function after the first point. Okay, so this is our energy function. If we make that 0, we satisfy the differential equation. And then we show in that paper that when you write down this formal measure, right? So you see here we say that the probability of this function of time is proportional to the exponential minus beta of the integrated square residual. That's what we say. And then you can show that this formal probabilistic statement over functions of time is the probability law, corresponds to the probability law of the following stochastic differential equation in the Ito sense, so traditional stochastic differential equation, where you see the drift term is basically given by the vector field, and then the volatility term, this BT here is Brownian motion, is basically controlled by the beta, by the inverse beta. Okay. And of course, the initial conditions of the SD has to start at that point. Okay, so why bother through this? I mean, why on earth would you like to do that? So first of all, it is fully Bayesian and it can in principle deal with very ill-posed problems. So think about missing boundary conditions, missing not having enough data to fully reconstruct your fields. Okay, that's one motivation. And in the case of biological flows, I'm going to show you at the end, this is exactly what we are. We don't have boundary conditions. It does not need a physical solver. It encodes the physical laws directly on the prior, and this is similar to pins. Okay. And it quantifies model form trust. If your physics are wrong, it's going to tell you beta, it's going to set beta to 0. So you will know. And if your physics are correct, beta will get a high value. But these are basically the three reasons why we're doing this. All right. So now I'm going to start touching on a few topics, a few key observations I want to make. So the first key observation is that the trust parameter is quantifying model form error. Now, Alex has a very nice theoretical example in one of his papers on arXiv where he shows that. So on the well-posedness of inverse problems. But I'm going to show you a synthetic example from Kairou's paper. So what we're going to do here is we're going to take a ground truth model that looks like that, sort of Lotka or Volterra equations. And it's a three-dimensional dynamical system. And we observe basically a noisy version of the state. And what we're going to do is we're going to take these quadratic terms and we're going to remove them from the calibration model. So we are purposefully constructing a calibration model that doesn't match the correct model. And we're going to generate synthetic data from the ground truth model, and we're going to apply IFT to estimate the state. So we're going to do two things: state estimation, so smoothing, what you would do with gamma filters or particle filters. You don't need this at all with IFT. IFT would do it for you directly. So we're going to estimate the state, and we're also going to estimate all parameters, A, B, C, D, and E. And we're going to do it for different values of alpha. So if alpha here, this alpha is 0, then we have a perfect agreement between the ground truth model and the calibration model, and the beta should go to infinity, so it should get a big number. If alpha is not 0, then we have a disagreement between the ground truth model and the calibration model, and beta should get a small value. Now, the other thing I'm going to show you is I'm going to apply to the I'm going to compare IFT to a traditional inverse problem where we're basically using Markov chain Monte Carlo, and in particular NUTS, no U-turn Hamiltonian sampling, to estimate the initial conditions of the dynamical system and the parameters. All right, so here's how we compare now the estimation, let's say, of just B. And in Kairou's paper, you can see these figures for all the parameters. So this is basically B, trying to estimate B. The correct value of B would correspond to this dashed line. And then here, each point, each pair of points corresponds to a different choice for alpha, okay, which controls the model form error, the discrepancy between the ground truth model and the calibration model. And for each alpha, we basically do NUTS, so MCMC, and we estimate the posterior over beta. And you see that for small alpha, when we have good agreement between the ground truth model and the calibration model, the posterior is very tight around the correct value of the parameter. But then as you start increasing beta, as you start increasing alpha, the model form error, look at what happens to the posterior. NUTS remains relatively certain about its inference, so it still has a tight posterior, but the posterior is not centered around the correct value anymore. It is centered around an arbitrary value. And this is a characteristic of Bayesian inference, of Bayesian asymptotics. Whenever you do inverse problems in a Bayesian way, you are silently assuming that the underlying forward model is correct. So you're doing everything conditionally on your model being correct. And Bayesian asymptotics in the limit of infinite samples tells you that the posterior will collapse to the maximum likelihood estimate. So basically, the NAT sampler will always give you a nice lump of samples around the maximum likelihood estimate, and that uncertainty will become arbitrarily small as you increase the number of samples. So this is undesired behavior if your model is wrong. It's desired behavior if your model is correct, but it's not desired when the model is wrong. Now, IFT does not suffer from the same issue. If the model is wrong, what it does is it actually increases the uncertainty in the posterior. Okay, so this is uncertainty about the parameter B, and if you're trying to use the wrong model, it tells you, well, you're using the wrong model, I cannot really estimate that parameter, and it increases the uncertainty. That is the desired behavior. Okay, let me show you what happens to the beta parameter, to the model trust parameter. So here I'm going to show you the point estimate of the beta parameter as a function of the number of variational inference iterations. And I'm going to show you that for different cases of model form error, right? So this alpha control the model form error. So alpha equals 0, no model form error, ground truth model, same as the calibration model. And you see that the model trust basically just monotonically increases as a function of the variational inference iterations. And if you keep going, at some point, it's going to become flat, but that will happen much later. Now, as you start increasing the model form error, you see that the beta grows with a smaller slope. Okay, so this is basically a higher error. This is even higher error. This is a higher discrepancy. And at some point, you see that beta basically just stays very close to 0. Okay, so this basically empirically shows you that with a synthetic example, that beta is in one-to-one correspondence with model form error, and that IFT can detect model form error on its own. All right, now I'm gonna make another point. So in both Alex's and Cairo's paper, we compare IFT to pins, okay? And it is very straightforward to see that if you take the IFT posterior and just take a log and put a minus sign in front of it, you basically get the traditional physics-informed loss function of pins. So we can say that pins, traditional pins, is the maximum a posteriori estimate of IFT. So pins are included in IFT if you choose to represent your neuron, your field as a neural network. Now, then you may naturally ask, what about Bayesian pins? What is the relationship between Bayesian pins and IFT? And there you can see that the log of the IFT posterior is the same as the log of posterior of Bayesian pins minus the Feynman path integral. So Bayesian pins and IFT differ in the Feynman path integral. The Feynman path integral is not in Bayesian pins. And the reason is because Bayesian pins put the physics in the likelihood, and we put the physics in the prior. That's what spits out the Feynman path integral. So the results of the two methods will differ if the Feynman path integral is important. Okay, and we have some examples that show that this is indeed the case. So this is a synthetic example against a Duffing oscillator, and we are observing noisy versions of the Duffing oscillator, and we're trying to estimate the state and these parameters, delta, alpha, and rho. And we use data from the blue interval, which you see here on the left. So the data we use are the data on the bottom, and we reconstruct the state with IFT. The state here is represented with Fourier series expansion. And on the right, you see the prediction. Okay, so there's no observed data on the right. It's basically a pure prediction. On the right part, you see basically the evolution of the posterior of the parameters delta, alpha, and rho. So basically, you do here variational inference over the parameters. This nested variational inference that Cairo came up with. And we use a Gaussian guide for delta, alpha, and rho. And you see how the guide starts at an arbitrary point and is gradually attracted by the correct values of the parameters. All right, so this is how IFT works. This is a prediction. When you try to apply Bayesian pins on this, you basically see that the predictions are not, the reconstruction of the state is basically perfect in both cases, but the predictions differ. And you see that the predictions of Bayesian pins is wrong. The difference is basically the Feynman path integral, okay? And if you look at the parameters, the estimation of the parameters, IFT at the top, Bayesian pins at the bottom, you see that delta is estimated correctly by both methods, but then IFT basically estimates all the parameters correctly, but Bayesian pins misses alpha and rho. So these are the parameters that exhibit to which the Feynman path integral exhibits sensitivity, and that's why you get something different. All right, so I made that point. The method is related to pins. Pins is the maximum posteriority estimate. Bayesian pins is basically IFT if you ignore the Feynman path integral. All right. Now we're going to start applying IFT to real data, actual dirty data collected by experimentalists. So this is an example where we apply the methods to make a model for the intake manifold of a combustion engine. This is work funded by Cummins, and the paper, Alex just told me today that it will be accepted. It's just working on a minor revision, so it will soon be available. So the intake manifold basically takes takes the combustion stuff and mixes it up and gives it to the different cylinders. Okay, that's what it does. And then we make a model of a simple thermodynamic model of the intake manifold that we want to calibrate on real data. This is how the model looks like. It has a temperature and a pressure and a differential equations for the temperature and the pressure. And then we have to estimate this heat transfer effects. And the heat transfer effects are modeled like this, and there are a bunch of parameters that we need to estimate. This H, the epsilon, and so on and so forth. Okay, we have to reconstruct the temperature and the pressure state, of which we only have noisy observations. So we apply IFT, and we let IFT find beta and all the other parameters. So it gives us here on the left, you can see the posterior samples from the parameters, and you see that beta is moderate. Okay, it's not like a million. A million would mean the model is perfect. 0 means the model is wrong. So it's moderate. We scale everything. That's why we can say that it is moderate. And so this means that the model is okay, not perfect, okay. And then you estimate the parameters with a little bit of uncertainty. And on the right, you see basically the prediction on a validation set. So this is a really dirty experimental data set, right? So you see that this is scale temperature. I'm not allowed to show you actual temperatures. Cummins wants us to basically scale the data before we share it with anybody. So these are arbitrary numbers scaled. The temperature is scaled so that the mean is 0, basically. All right. And this is what happens when we use the incorrect model. So we introduce a something that is wrong in the model. So assuming that there is EGR, like the gases are basically recirculated. And when we do that, we get a much smaller beta, which is an indication that this assumption is wrong. And this is also reflected in the posteriors over the parameters, which are broader. And of course, the predicted distribution for the temperature is pretty much all over the place. All right, and this is a direct comparison of the two cases where we have two different models and we're assessing which one is better, and you see that the model with a smaller beta is what the method tells us is better, and it gives us also tighter posteriors for the parameters. But even the orange model, you cannot really say that it's perfect. All right, I'll show you another example. So this is Bayesian identification of thermal conductivity of fibrous insulation with information field theory. This is also a paper that Alex is writing right now. This is funded by the Air Force. And basically, we were studying the insulation that you put on re-entry vehicles, so vehicles that basically enter the Earth, and they exhibit really, really high temperatures as they enter the Earth, and sometimes they also go with hypersonic speeds. And to protect these vehicles, you basically use material that looks like this. It's called fiber insulation. So you put it inside the structural layer to protect the heat from basically going through the entire thing and burning it. So we have a project with Air Force where we are collaborating with people that manufacture this material, and we're doing the UQ analysis of the material. Now, in collaboration with Cameron from NASA, we try to understand the thermal conductivity of these materials so that we can run re-entry simulations. So Cameron set up this experiment where he tries to measure the thermal conductivity. So he takes this fibrous insulation and he puts it between two plates. There's a cold plate and a hot plate, and he controls the temperature at these two plates, and he basically has thermocouples inside at various points of the thermal insulation, and he measures the temperature. So the inverse problem is from the measurements infer what is the thermal conductivity of the material. Now, at these extreme temperatures, the thermal conductivity is not constant. It is a function of temperature. Okay, that's what it is. So you have to recover a function of temperature, a conductivity that is a function of temperature. This is the physics that govern the system. It's basically 1D physics, but notice that the thermal conductivity is a function of U. It's a nonlinear physical equation here, and you have to simultaneously infer from a single experiment, basically infer K as a function of U, the temperature. And what we do is we take these physics, we turn them into an IFT prior, and then we model the thermal conductivity, which is a function of U, as a Gaussian process with a linear mean and some covariance function. Alex takes a square exponential, and then we have a measurement model that connects the temperature to the measurement by the thermocouples. This is the standard Gaussians. And then we write down the joint posterior of U, the temperature field, and K, the thermal conductivity function. And then we apply IFT, stochastic gradient algebraic dynamics, to characterize the two after we parameterize everything, of course. All right, so here on the left, you see the calibration data, and you see basically that IFT reconstructs the temperature field perfectly. It exhibits a little bit of uncertainty. So left is the temperature as a function of length or depth in the fibrous insulation, and on the right you see the inferred thermal conductivity function as a function of temperature. And here you see why we're doing this experiment. The experiment cannot go to the temperatures that this reentry vehicle will experience. So you have to make a model. You have to make some measurements at the range where you can do them, and then you need to make construct a model that can confidently extrapolate to really high temperatures that you cannot emulate in the lab. So, of course, we cannot have the temperatures we cannot emulate in the lab. We can only have the temperatures we can emulate in the lab. So we cheated a little bit and we removed part of the experimental data that we couldn't see. So we removed really high temperatures. And in this way, we were able to see whether or not what we get with IFT can extrapolate correctly to higher temperatures. And the agreement is pretty good at the beginning, and then you see that IFT basically assigns higher uncertainty interval for temperatures that are well above the ones we experimented with. And then once you have constructed this uncertain or probabilistic thermal conductivity model that characterizes thermal insulation, you can use it to do reentry simulations. And we have here reentry simulations with uncertainty for Mars and for Earth. You just see here the uncertainty in the temperature at different points of this of a reentry vehicle, right? So you see here the top layer is basically the boundary condition that we impose to the vehicle, and then the internal point right here. This is the point where your electronics start feeling the temperature, and this is what you want to protect. So you don't want a temperature to rise too much. And you see here that the predictions are good for the first points, but then because of the uncertainty in the thermal conductivity, the uncertainty grows as you go towards this point. Now, you don't have to have a perfect model to design good insulation for these hypersonic reentry vehicles. So that's actually, I mean, you can have a safety factor and say, I'm just going to use more of that material, and it doesn't matter that I'm uncertain. Okay, you just want to make sure that you don't hit a high temperature that is going to melt everything. All right. Now here's an application that Alex has been developing that is actually very preliminary, but is very likely to change things in Bayesian deep learning. And I'm not exaggerating. I think it's a really cool idea. And I'll show you some preliminary results and why we think this is good. So let's say you want to do Bayesian deep learning. What do you typically do? You go and you take the weights of your neural network and you put some Gaussian priors of the weight, like independent Gaussians on each one of your weights. And then if you sample from this and you visualize your neural networks, you will see that they basically look like garbage. Okay, there's no way you can encode prior beliefs about, let's say, the variance or the smoothness of these functions but by just using Gaussians on the neural network weights. And if you look at the covariance kernel that you would get in the infinite width limit of a neural network, of a Bayesian neural network, you will see that this is the covariance you get, which is a covariance that basically doesn't mean anything. Okay, it depends on your activation function. So unless you want to go and really tweak your activation function so it gives you what you want, you really have no way of controlling what kind of sample functions you get from a Bayesian neural network. So the idea was basically to use information field theory to construct a prior over the space of neural network parameters that comes from a Gaussian process. So basically, if you like, we take a Gaussian process and we try to project it to the space of neural network parameter distributions. Or another way to say it, we take a Gaussian process and then we try to construct a probability distribution over the parameters of a neural network so that if we sample from this probability distribution and we visualize the neural network, it basically gives us a sample from the Gaussian process. And this has tremendous benefits. So first of all, it has benefits for the theory of deep learning because you can use this idea to endow neural networks with Gaussian process priors, which is great. You can encode smoothness, you can encode variance, length scales, and so on, periodicity. You can say I'm having multiple length scales. All the goodies you can do with Gaussian processes, you can now do them with neural networks. And the other implication is in the theory of Gaussian processes. So in Gaussian processes, you have to do all sorts of tricks to deal with really, really large data sets. But if you make this connection between Gaussian processes and neural networks, you can use neural networks to represent samples from Gaussian processes, and you can potentially do Gaussian process regression or other tasks that involve Gaussian processes with really, really, really high or large numbers of samples. All right, so here's the idea. We take the covariance function k, and we make this operator that is basically just applying k to u. So here this should be a typo. This should be a u here. So this should be integral of u of x prime kx x prime. And then this is the probability measure. This is the IFT probability measure that we assign to u, which is the function. And it's basically just an inner product, a traditional L2 inner product between the function and this, the inverse of that. And then we parameterize u with a neural network, and we look at the induced probability density over the neural network parameters, which looks like that. And we can show that in the limit of infinite neurons, or infinite width limit of neural networks, the probability measure that we have constructed over the space of neural networks basically converges to the Gaussian process. The Gaussian process we wanted, not an arbitrary Gaussian process. Now, this is preliminary results comparing basically the samples we get in this way for a specific covariance function that gives us Brownian motion. So there's a Brownian motion is a Gaussian process, and there is a specific covariance function that gives you Brownian motion. If you use that covariance function to construct probability measure over the space of neural networks and you sample from them, you can get neural networks that really look like they're sampled from Brownian motion. And if you look closely at their statistics, like the empirical statistics, and you compare the empirical covariance of these samples to the true covariance corresponding to Brownian motion, they're the same. And if you look at the marginal, they're also the same, the marginal distributions. And this is another preliminary example where we take a neural network, a Bayesian neural network, and in the left case, we basically do regression with the data set you see here using a periodic kernel. So we can encode the assumption that there is periodicity in the neural network parameter prior. And here on the right, you see the result you would get if you just use independent standard normals on the weights for the neural network parameters. Okay, so these are I would say simple examples of IFT. Now, on more serious examples of IFT, we're getting into biological flows. And I'm not really gonna go over that because I want to give you guys the chance to ask some questions. I'm just gonna mention that there's a paper on arXiv called SMaRT. Has been pioneered by Atharv, and also Abhishek has been helping a lot. and to push the method forward. And all the data you've seen, I'm gonna flash are collected in collaboration with Pavlos Vlachos, who is a professor at Purdue, but is also a vice president of research at Lilly. And the work is funded by Lilly and NSF. It's the theory primarily funded by NSF, and the applications are funded by Lilly. But I'm not going to show you the Lilly applications because I can't. So anyway, the idea here is to use IFT to reconstruct um, biological flows. So this includes the following things. So from MRI measurements, reconstruct the geometries of the biological objects. So here you see a moving heart, and we want to reconstruct the geometry from the MRI images. And this is called geometry. It calls the segmentation of geometry, which is usually done manually. And we also want to reconstruct and super resolve the velocity field, and we also want to reconstruct the pressure. So the results I'm going to flash are basically with a maximum likelihood estimate from IFT, and we're currently working on the on sampling from the posterior with physics. It works, but it just takes forever, and we're trying to improve the scaling of the algorithm. All right, so there are various applications, intracranial flow. This is a three-dimensional aneurysm that we use for validation. Pavlos 3D group 3D printed the aneurysm, and they do PIV experiments, particle image velocimetry, to reconstruct a ground truth we can compare against, and the method works quite well. You can find it in the paper. And really, I'm just gonna flash it. Okay, there's no time. I really don't want to take the full hour. This is a reconstruction of the motion of the fluid in the intrathecal space. This is inside your spine. So basically, these two regions, the cervical vertebrae and the lumbar vertebrae. This is actually one of the first times someone visualizes this kind of flow at this detail. We're using this with Lilly to understand how drugs transport when you inject them in the spine, how they transport to the brain. Another application is cardiac fluid flow. Here we try to reconstruct the whole heart and whole moving heart without any prior knowledge of the geometry and without any human intervention. Okay, there's no human labeling anything. And it kind of works, but it's not perfect, but it's an improvement compared to the result you get from MRI. All right, so if you want to see more about that, the person to invite is Atharv Hans, also my postdoc. He's basically the person who has developed this method we call SMaRT. All right, and with that, I'm gonna stop here. Thank you.
Thank you, Ilias. I'll probably open the floor for questions.
Maybe I can quickly start and then go to the audience. Rajdeep has his hands raised. Maybe let me start. So, yeah, I mean, I have so many questions. Let me ask one or two. So the GP, right? GP prior for neural network. So that was the idea. I think functional prior also uses some kind of similar idea. So is this functional prior a special case of this IFT or vice versa? Is there a relation between the two?
So Alex is investigating this relation, but it's I can confidently say that our way is sufficiently, let's say, different and perhaps more flexible.
Okay.
Okay, but we will have to wait for the paper where he will have to compare to other approaches.
Yeah, sounds good. And the other question is, how does it, I mean, this is a very old question actually. So So what are the stochastic dimension of the problem, the inverse problem that you are solving? I mean, the dimension, how does it scale? We know, right, MCMC and all those things does not scale for high dimension and all those things. Like if you scale expansion in one problem I saw, but how does it scale with the number of random variable or number of variables in general?
Yeah. So here, to give you an idea, in this kind of problem you see here with the heart, the dimension is really, really, really high. Like basically imagine how many parameters you need to represent a geometry that is moving like this. Sorry. A moving geometry, and also the velocity field, and also the pressure field. These are the unknown quantities, so really, really, really high dimensional. So we represent these with neural networks. And when what you see here is the maximum likelihood estimate. So the maximum likelihood estimate, it scales. So we can get these results in a few minutes in A100, the H100 GPU. Like probably the analysis you see here takes like 5 to 6 minutes. Now the sampling from the posterior does not scale yet for this problem. Okay, like they're really high dimensional. Like to get like 1 million samples from the posterior, we do probably 15 hours of H100, and this gives us 100 effective samples, right? So we do 1 million iterations to get 100 relatively independent samples. Takes 15 hours. So we're trying to improve the sampling algorithm from something like stochastic gradient algebraic dynamics, the simplest thing we can do, to other ideas like energy conserving Hamiltonian Monte Carlo with some subsampling, or preconditioned stochastic gradient algebraic dynamics, or maybe even go to variational inference. So I would say IFT for dynamical systems, you have a few 100, 200, 300 parameters, maybe even 1,000 parameters, is okay, it's doable. This where you have millions of parameters or tens of millions of parameters, not yet there. I mean, unless you want to spend like $5,000 on every problem and wait a few and wait for a week. Yes.
Yeah. No, that's yeah. But it's excellent actually. Yeah, maybe others can ask question. I'll not take much time. It might be short on time. Yeah.
Okay. Ravi, you wanted to ask something?
Yes. First of all, very nice work, especially the last one. I think has definitely a lot of potential. My questions were mostly about this framework where you're forming this energy, right? And then you have a kind of a discounting factor or trust factor, as you would like to call it. All right. So, so this trust factor, is it like, for example, in the case of Bayesian posterior, there has been a lot of these kind of factors where instead of the likelihood, they kind of tempered likelihood, like a temperature term on the likelihood that would actually kind of simulate your trust in the model, stuff like that. Even there has been in modern times something called as generalized Bayesian inference, where they say that you can replace the likelihood with any loss function that you want. It's completely fine. It still is a so not just leaving about the function part of it. Is that so? This beta that you introduce, how do you, so for a person who doesn't know how much to trust the model one has, how would you actually go about choosing this beta?
So let me answer in two ways. So first, this paper right here, the paper on the, okay, sorry, for some reason I'm gonna have to make a new slide. Wait a second. New slide. Here we go. I hate to waste everybody's time. Okay, so this is the paper on the well-posedness of inverse problems under information field theory, application model error detection. This is the paper where Alex and I explain theoretically what this beta does. And we argue about how you can potentially choose it. Okay. And it has to do with basically it has to do with the discretization of the problem, like how many parameters you use to represent your function. Like the more parameters you use, the higher the more evidence you will have that the model is correct to pick a big beta. And the answer that we give is you have to scale the problem, and then the beta is inversely proportional to the number of parameters you're using, okay, to parameterize your function. But the best thing to do is to not make a choice. So you let Bayesian inference tell you what that beta is. And if your model is correct, it should grow, not indefinitely, because I mean we saw in this paper that it should go to infinity if your model is perfect and you have infinite data. But guess what? You never have infinite data and your model is never perfect. So it will never go to infinity in reality. But you should just let it settle on whatever it wants to be, basically.
Okay.
Okay.
So I have a second question, probably the final question before I let others. So that was regarding, let's say, in a mechanics problem, I might be more uncertain, let's say, about the boundary condition, but not so much uncertain about the, let's say, the constitutive model. So if I'm, let's say, more uncertain about the boundary condition or maybe the initial condition, how can I treat the trust parameter? Because the trust parameter, it sits in front of an energy function. And as I understand, the energy function has to probably given as a integral of the entire dynamics, which might as well include the boundary condition. But if I, let's say, have more of a trust issues with the boundary condition, not so much with the equation, let's say the thermal conductivity nonlinear equation. I'm very sure about that, but not so much sure about the boundary condition. How would I be able to kind of impose this kind of an uncertain boundary condition?
So you use hierarchical Bayesian modeling. Like here in this example, for example, the initial condition is an unknown. And then the physics is conditional on the initial condition. And so if you look at this expression here, right, it basically tells you that the probability of the state after the initial condition, given the initial condition, follows this. Okay, so now you just go and you put a prior over the initial condition.
I see.
That's all.
Okay.
And
the same way I can.
Here you put a prior over the boundary, and then condition on the boundary you have a prior on the physical field. So you use a hierarchical Bayesian approach.
Got it. Okay. Yeah. Thanks a lot. That's all, Sunita.
Okay. Thanks, Ilias. Let me quickly check with the audience if anyone has any question.
I think we went a little bit over time.
Yeah, that's okay. That's okay, Ilias. This is wonderful.
That's fine.
Yeah. I think I'll reach out to you with my questions probably in the email. We can stick to 10 minutes excess. That's fine.
Sounds good. And if anybody wants to ask any questions, please feel free to send me an email. I most probably will just forward your email to Alex.
On that same note, Ilias, we are going to reach out to Alex to give a detailed talk on the IFT work.
Sounds good.
Yeah.
Okay.
All right.
So thank you so much, Ilias, for joining us.
Take care. Bye-bye.
See you. Bye.
Bye.